Now, the part before this talks to you about how you actually got your induced EMF and induced current. If you want to explain the magnitude of your induced EMF, you want to explain the direction of your induced EMF, you would have to use two specific laws. Okay, those laws are your laws of electromagnetic induction. So the first law that you have to refer to usually is Faraday's law. Faraday's law explains to you the magnitude of your induced EMF. Faraday's law states that the magnitude of the induced EMF is directly proportional to the rate of change of flux cutting or rate of change of flux linkage. Later on, when you do your partial questions, you will notice that Faraday's law can also be somehow shortened to just magnitude of induced EMF is directly proportional to rate of change of flux. In the older marking schemes, they would have said it as directly proportional to rate of change of flux cutting or rate of change of flux linkage. But in the more recent marking schemes, they shorten it, where they just say that Faraday's law states that magnitude of induced EMF is directly proportional to rate of change of flux. You can also write it this way. Just write either term would be sufficient. But the key thing is that you must say it's rate of change. Now, a rate of change of flux, as I mentioned, always produces an induced EMF and consequently an induced current. If you want to summarize this law in the form of equations, there's usually two forms of it. If you're talking about a single wire, this one usually relates to flux cutting by a wire. Your EMF induced E is equals to change in flux cutting divided by your time. And then for coil with N turns, this one usually refers to flux linkage. Your EMF induced is equals to the rate of change of flux linkage. The only difference between this equation here with the previous one is that you have the N there. When you have the N there connected with your flux, it's actually referring to flux linkage. This first equation here is talking to you about rate of change of flux. The second one is rate of change of flux linkage. So you will notice also that there's a negative sign to your equation. The negative sign actually denotes to you the opposition of induced EMF due to Lenz's law. This one will be the next thing we'll be talking about. Now, what is Lenz's law in the first place? Lenz's law tells you the direction of your induced EMF or your induced current. If Faraday's law tells you the magnitude of your induced EMF, Lenz's law tells you the direction of your induced EMF or current. It states that the direction of any induced current is such as to oppose the flux change that causes it. Oh yeah, one thing to mention to you here is when it comes to Faraday's law, a lot of times we often use current and EMF interchangeably. But when it comes to Faraday's law and you want to write down the definition, just be very careful about this. Faraday's law really talks about induced EMF only. Induced EMF being proportional to rate of change of flux cutting, rate of change of flux linkage, or rate of change of flux. If for some reason you write the definition of Faraday's law as magnitude of induced current is proportional to rate of change of flux and similar to that, this would be considered as wrong. Because Faraday's law isn't talking about magnitude of induced current. It's talking about magnitude of induced EMF, induced voltage. Just now I told you that current and voltage are two different quantities, but they are closely related. In your case here, Faraday's law is really specific only for voltage or EMF. You should not be putting in induced current inside your definition because that one is considered as wrong. So for Lenz's law, if you had said that the direction of induced EMF or induced current is such as to oppose the flux change that causes it, that one is fine. Current and EMF here, this one, you can put it here. Lenz's law was really only talking about the direction. Unlike Faraday's law, it was talking about magnitude. It was more specific to a particular quantity, which is your voltage. All right. So Lenz's law is actually a consequence of the principle of conservation of energy, which states that energy cannot be created but converted from existing forms of energy. All right. When you have an induced current, it actually represents to you electrical energy inside the wire, which will eventually be converted to heat energy, because as current flows through your wire, it will actually heat up the wire. So that would have meant that heat is generated. So that's why here we say your induced current is actually electrical energy, but it's eventually converted to heat, because the induced current will heat up the conductor that it is flowing through. So let's just consider two examples here to see why Lenz's law is actually a consequence of the principle of conservation of energy. Say you have a magnet here, and then you have a solenoid. If you were to push your magnet in, from the example that we've just done 1 or 2 pages back, if you were to push your magnet in, the magnet here actually has its own magnetic field or magnetic flux. If you were to push your magnet into the solenoid, you could say that there's flux cutting of your magnetic flux by your solenoid. You could also say that there's actually a flux linkage change of your solenoid. Either way, you will still get an induced EMF and subsequently an induced current. But when it comes to the case of a coil, your induced current can flow in two possible directions. It can be flowing like this, or it can be flowing like this. So which is the correct direction in the first place? So let's just consider that your induced current is trying to flow like this. You learned that in the previous chapter for magnetic field, when you have current flowing through a solenoid, it will tend to produce its own magnetic field. So right now, apart from your bar magnet here, which has its own magnetic field like this, current flowing inside your solenoid would also produce its own magnetic field like this. So when your solenoid produces its own magnetic field, there will be a polarity to the magnetic field, where one end is north, one end is south. So let's assume that right now, for the current flow flowing in this particular direction, you get a magnetic field where the polarity is south and north over here. So let's consider this then. Your magnet has an N pole here, and your magnetic field produced by a solenoid is an S pole here. So what is the nature of the force between those two poles? You would say that the nature of the force is actually attractive, isn't it? When you look at the force acting on the magnet itself, because the nature of the force is attractive, there's actually a magnetic force acting on the bar magnet in this direction. So from there, if you have a magnetic force acting on your bar magnet right now, that would mean that your magnet is actually going to be pulled into your solenoid. When it's being pulled into the solenoid, it's going to cut even more magnetic flux. It's going to cause even more induced current, which in turn causes you to have even more electrical energy, right? So right now, it seemingly looks like that you're getting electrical energy out of nothing. Because you see, if you have a magnetic force here, there's no need for you to purposely apply a force F to push the magnet in. Because there's already a magnetic force here that will do the work for you. So you just give it a little nudge, and then after that, you cause an induced current in your solenoid, then that solenoid will exert an attractive force on your magnet and will pull your magnet in. So as the magnet is being pulled in, it will cut more magnetic flux, it will cause more change in flux linkage, you're getting even more induced current, more electrical energy here. So it seemingly seems like you're getting energy out of nothing. That's the reason why this current direction would have been considered as incorrect. So let me just reiterate what I've just mentioned by looking at some of the points inside the notes here. So here, current direction is such that the magnetic field produced by the coil has an S pole facing the approaching N pole. The poles attract one another and the magnet will be dragged into the coil without the need for any external applied force or input energy. So that magnet will now accelerate into your core because there's a force, there's a net force. It accelerates, it speeds up, which then causes a greater rate of change of flux linkage or flux cutting. You have now a higher induced current produced, which then causes an even stronger attraction between the coil and magnet, and then a larger flux cutting or flux linkage here, which then causes an even increasing induced current. So it seemingly seems like the energy will keep increasing. All right. So this goes against the principle of conservation of energy because right now you seemingly have electrical energy created out of nothing. And at the same time, your magnet has also gained kinetic energy. So where did those energy actually come from? It cannot have just come from nothing. All right. So that's why here, if your current direction is like this is wrong. So let's consider the other opposite case then, where this time, rather than having the current flowing like in the first diagram, your current direction is now like this. So you have current in the opposite direction inside a solenoid. You're also going to produce a magnetic field, but because the current direction is opposite direction now, you're going to get an N pole here and an S pole here. So now when you then consider the interaction between the poles of magnet here and here, because this is north and north, this is going to be repulsive. There's going to be repulsion here, repulsion here. So what you're more interested in is the magnetic force that's acting on your magnet itself. So see, from here, your induced current inside a solenoid causes a magnetic force that's trying to oppose your magnet from going in. Okay, so in such a case now, if you wanted to continue to have an induced current, you wanted to continue to generate electrical energy, this would happen that you would need to purposely apply some sort of force to overcome this magnetic force so that your magnet can eventually go in, cut magnetic flux, cause flux linkage change in order to cause induced current. Now, in such a case here, then, because you had to purposely apply a force to push the magnet in, this means you're doing work. So if you try to relate it to conservation of energy, this would then tell you that the work that you have done has actually been used to generate electrical energy. This one would follow conservation of energy. So this current direction here is actually more sensible. It's actually the correct current direction. So again, you look at the notes. In this current direction causes magnetic field produced by the coil to be an N pole facing the approaching N pole of your magnet. These two poles repel one another, causing work to be done to push the magnet into the coil. Thus, energy is transferred by the work done into electrical energy as well as kinetic energy. So here, conservation of energy is obeyed. This one is one example of Lenz's law in work. It's basically trying to make the induced current follow conservation of energy. Now, there's another case on the next page. This one, rather than talking about a magnet that's being pushed into a solenoid, you have a straight wire being pushed down through a magnetic field by applying a force downwards into it initially. So here, you have your magnet with its magnetic flux, and then you have your wire. You push it down in this direction. From the example a few pages back, we already know that because you have flux cutting here, you're going to have induced current. Okay, now same thing as before then. How do we know what is the direction of your induced current? Your induced current could be flowing in this direction, or it could also be flowing in this direction. So Lenz's law will tell you which direction is supposed to flow. Lenz's law will explain to you that there's only one correct direction for which your induced current can flow. All right. So right now, let's consider your diagrams on the left-hand side here. If your case here is that you say that you have an induced current going in this direction, your current is in this direction. From Fleming's left-hand rule, by right, this wire itself should also have a magnetic force acting on it. Okay, because right now, if you consider this wire having an induced current, this current flowing through your wire is actually under a magnetic field produced by your magnet here. So right now, you can actually use Fleming's left-hand rule to predict that there's actually a magnetic force acting on this wire here. Where right now, if your B is in this direction, your current is in this direction, your magnetic force will therefore be downwards, which is actually indicated right over here. So let's consider this then. Your magnetic force is in the direction in which the wire is being pushed down. This was your direction of motion. So if your current direction was going in this direction, because you're going to generate a magnetic force acting downwards in the same direction as your motion, this again would have implied to you that the moment you have a magnetic force generated here, you again do not need to purposely apply a force to push the magnet down. You can just let the magnetic force do the work for you. So when this magnetic force does the work for you, it will accelerate your magnet downward, causing an even greater rate of change of flux cutting. So you're going to get more induced current, you're going to get more electrical energy. Again, seemingly out of nothing. Your induced current increases further, and there's again gain in kinetic and electrical energy for seemingly no energy input, which contradicts principle of conservation of energy. So again, this one will be the incorrect direction. The other correct direction then would have been the second diagram here. So why is it correct in the first place? So same thing, you push the magnet down so that it cuts the magnetic flux of the magnet. If you say that your induced current is in this direction, the direction of your magnetic field is in this direction, according to Fleming's left-hand rule, your magnetic force will be outwards. So let's consider this then. Your wire now has a magnetic force acting upwards here. So if you want to cut the magnetic flux, because you have a magnetic force here, this would mean that you need to purposely apply a force downwards to push the magnet down so that you can actually cut magnetic flux and cause induced EMF, induced current. So if you have to purposely apply a force to overcome this magnetic force so that you can push the wire down and cut magnetic flux, this means that you have done work, and that work that you have done must have been converted into the electrical energy or your induced current. So according to conservation of energy, this one is again the correct direction. So your induced current must flow as in figure B here, so that the magnetic force produced acts against the external force applied to push the wire down. You would actually now have to do work to move the wire against the magnetic force, which is then converted into electrical energy or induced current, thus following principle of conservation of energy. So this is you trying to understand Lenz's law in terms of conservation of energy. Lenz's law is basically trying to tell you that your current direction flows in one particular direction only because it's trying to obey conservation of energy. But usually in your exams, when you want to apply Lenz's law to explain your question, you usually don't really use like the explanation that's given inside your notes here. Instead, you tend to use a different interpretation of it, like what is being shown in your next page here. Lenz's law states that the direction of induced current is always such as to oppose the flux change that causes it. It can be thought of in another different way, where you say that the direction of induced current is always such that it will make the magnetic field to oppose the flux change that causes it. The one in your notes, the definition was direction of induced current is such as to oppose the flux change that causes it. This one here is basically based on the same thing. It's just that here we add something else. is always such that it establishes a magnetic field to oppose the flux change that causes it. This is just adding something extra in between. Now, why do we say that your induced current is such that it opposes a magnetic field to oppose the flux change that causes it? You look at this example here again, which is basically your solenoid having a bar magnet being pushed into it. So we know that when you push your bar magnet in, it's going to cause flux cutting or change in flux linkage. Thereby, you're going to get induced EMF or induced current. So here, when you start pushing your magnet towards the core of the wire, current is induced inside the core due to an increase in flux linkage of the core. So here I'm explaining the EMF induced as due to an increase in flux linkage. Before your magnet was being pushed in, there's no flux. But once your magnet is pushed in, there's an increase in flux linkage. You therefore have EMF induced. So Lenz's law says that you are going to oppose this flux linkage because the flux change that cause your EMF here is an increase in flux linkage. So Lenz's law says that whatever you do, you will try to oppose this increase in flux linkage. So how is it going to oppose the increase in flux linkage here? All right. The induced current will flow in such a way that it now produces a magnetic field that opposes the magnet from being pushed into the core. When it does so, it is actually trying to oppose the increase in the flux linkage of the core. Earlier, you know that there's going to be an induced current flowing inside your solenoid here. The direction of induced current will be such that it opposes the flux change that causes it, right? More specifically, it causes a magnetic field such that your magnetic field has this polarity, north and south here. So when you have a north pole here, it's actually opposing the north pole of the bar magnet. So it's actually going to oppose the increase in flux linkage of the core because it's trying to push the magnet out. So that's why here, Lenz's law, you can think of it as something like this, where your induced current tries to make a magnetic field to oppose the flux change that was causing it in the first place. If your case here is that you have an increase in flux linkage, Lenz's law will say that you are trying to oppose that flux increase. The only way you can oppose that flux increase is if this one is a north pole here. So here, the core end closest to the magnet becomes an end pole to repel the end pole of the approaching magnet. Now, what about the case then where you try to pull your magnet out? When you try to pull your magnet out of the core, away from the core, you again would have induced current because you still have flux change here, but your flux change is a decrease in flux linkage because your magnetic flux is trying to leave the core, you're having a decrease in flux linkage. So in your case here, you have flux linkage decrease, therefore your EMF is also induced. But the direction of induced current inside a solenoid now still needs to obey Lenz's law. So here, your induced current direction, when compared to the first diagram, will reverse so that this time the magnetic field produced opposes the magnet from being pulled out. So now you have an induced current flowing inside a solenoid. It again establishes another magnetic field around the solenoid, but this time it will be south pole here and north pole here. So that if this one is south and this one is north, the bar magnet will actually experience a magnetic force that's trying to pull it back in. When you have a magnetic force that's trying to pull it back in, This is actually trying to oppose the decrease in the flux linkage of your coil. So your induced current now is in such a way that you have a south pole here, so that you exert a magnetic force to prevent or to slow the magnet from going out, because you're trying to oppose the decrease in flux linkage here. The coil end closest to the magnet becomes an S pole in order to attract the N pole of the retreating magnet. Okay, that is what we mean by Lenz's law, establishing a magnetic field to oppose the flux change that causes it. So under both cases, you can see that Lenz's law is actually trying to stop the magnet from moving actually. It was because the movement of the magnet caused a flux change. Your Lenz's law is actually trying to stop the magnet from moving so that your flux change doesn't occur. Okay? So this is in general how Lenz's law works.